Okay, yeah, we are in live. Good afternoon, everyone. Welcome to the next module, binary exploitation. Welcome to the next class. Hope you have done you completed the web security. So we are starting with the next module from today, and this is the last module, and it closes in 1 week exactly on Sunday next week, and next week would be the last week for our semester. Hope you enjoyed the course and the challenges, and and I believe that you benefited a lot from this different delivery method of doing everything using only hacking. As mentioned, we don't have exam, so all the grades would be based upon uh, the the hacking challenges, and you should ensure that you have linked your Discord and the ASU ID so that the grades has been reflected and being correctly uploaded to your course rosters. If there is any question regarding the challenges regarding the course delivery and administration and logistics, let me know. And with that, we can. There are once again. Yes. If there are any, let me know if any questions related with course logistics or the administration. If not, we can move on to the uh, today's module. So, if you can remember that we introduced, I hope you were able to complete up to the challenges 13 and 14. I think we slightly hinted um, uh, about the cross site forgery, request forgery, um, and subsequently the other challenges 13 and 14 also would be using similar to that, and I believe that you are able to complete that. And from today's we are going to move on to the binary exploitation. What we mean by binary exploitation, we exploit the vulnerability at the binary level. So we just on the last module we introduced about the injection type of attacks, and we saw different types of injection attacks. So we started with the command type of injection, in which we will use to exactly use we would be trying to inject the commands to the OS uh, using by spawning the shell command, like exe cve that we are seeing in the slides now. And we saw SQL type of injection, through which we will be able to attack the vulnerability on the server side. And then on the last week, we saw about the script side, cross side script attack that would be done from the client side. And this is about front end JavaScript side of script based injection attacks. And we mentioned about the stack attack and the OS type of attack. Those would constitute something more closely related to the binary exploitation that we are going to see from today. We have three lecture schedules, and uh, hopefully we will be able to cover all the one. So let me open the uh, dojos. We have the module is due by Sunday exactly, next Sunday, 11 days in 11 hours. And we have around 22 uh, challenges that covering the shellcode injection, memory errors, and the buffer type of attacks. And then at the end, we will go over a little bit about the program exploitation. I think from for today's lecture, we will concentrate on the shellcode injection, uh, and so the binary exploitation would cover a yeah, wide range of topics uh, that includes the memory type of attacks uh, and the shellcode type of attacks. That would be the topic of the concept for the today's one. So we will go over other kind of things like buffer overflow and other things uh, probably from the next class. And the shell code also involves the buffer overflow. So it's something like a smashing of the stack such that you would be able to change or modify the return address and you inject your own code using the by exploiting the vulnerability and get complete control over the system. So the binary exploitation gives the complete control compared to the script type of injection, the SQL type of injection that we saw in the last week. So you would be restricted to the technologies and the application level, and the script at the script proficiency, the script capabilities that it can provide. Once you get to inject, get the vulnerability and able to get into the binary level, you have the flexibility to have a complete more control over the um, victims systems. Uh, and that would be the topic for today's and specifically for the shell code injection in which you would be able to spawn a shell and with your payload of your you would be able to make a complete uh, control over the systems by using the shell. And once you have the get control over the shell, since the program would be running from the root folder, and if you can from the program, if you find a vulnerability and using that vulnerability, if you can able to spawn a shell, then you have the complete control over the system, because the program would be executing from the as a root privileged authority, and the shell spawned from the program would also have the root privilege, and you would be able to make a complete control over all the resources on the victim side. So that's the major advantage of going from the binary exploitation perspective. Let me open the slides. So I'll open the slides by Professor Yan, which gives a complete, which gives a very good introduction to the flight control. Yes. So what do you mean by shell coding? So in the context of binary exploitation, as I mentioned, binary exploitation is attacking the program or the system by using the vulnerability from the binary level. So the shell coding involves crafting a payload that can be injected into the shell and getting the complete control over the shell. So you will spawn a shell using using some vulnerability that you find from the binary uh, code that's delivered to our software, and from the once you get control over the shell with the payload of specific crafting of the shell, you make a complete control over the shell and you get the resources that you want to achieve. So that's the shell coding is about. um, the slide that you see here, we have two kind of architectures in computers, or that's one called von Neumann architecture and hardware architecture. What do you mean by von Neumann? What's the von Neumann architecture is that both the program and the data are stored in the same memory. We don't have, and in contrast, hardware we have separate memory for the program or instruction and the code. And most of all of the more popular instruction are one Newman type of architecture in which both the program and the data stays in the same memory. Uh, so and this gets the rather opportunity or potential risk of the code getting into the getting being interpreted as data, or the other way around, that data being interpreted as code, or be injecting a code as a part of the data and being get executed, getting control over the um, uh, uh, compromise the victims. Um, and there are hardware architecture also, as you can see here, AVR, but they are slightly few, and there would be a different kind of attacks that we have to think for it. Um, Sorry, here it is. So what's the shell coding is about? So the shell coding is about, if you can remember from your previous courses that you have gone over, for example, the CSE 340 principles of programming languages. You will have a stack that will have, for every program you would have the instruction, and then the stack that contains the data specific to the program, and for this heap that would be created by the process OS processors for uh, specific type of memory for the specific type of model. The temporary variables, the return address, and the arguments and other kind of, for every function call will be stored, would be saved and opened with a stack, and the instruction would get that we call by context, and each program and the function call would have the context with the data specifically residing in the stack part, and user defined created memory would be stored in a heap part. What if it get mixed up? So if we can able to inject the code inside the, as we saw in the one human architecture, the data part and the kind of instruction part also stays in the same data. And if you can able to inject the code inside the stack, the processor would uh, execute the instruction that is available in the stack, and you have your the payload, what are the objective that you are intended for that payload being getting executed from the being injecting into the stack. So that's the concept is about the shell code. So for example, the code that you see here is an example um, uh, code that says hello world code that invites you with the welcomes you with the hello your name, and then with a message of farewell. So you can see here, it has the buffer or array of name to get the string of characters, and that gets the name, and then it prints the hello. So the function of the hello is nothing but you pass the name that you get from the user input that's stored in the array buffer, string of array, string name or array of characters, and then the function simply just prints out the goodbye. And if you can see here, uh, what we see here, we are printing, we are just mixing up the arguments. So 50% of the time, so this is nothing but we are generating a random number, and if we modulus by 2, that's something around 50% of getting whether it's an odd or even. So 50% of the time, this would get executed, in the sense the first argument would be the function pointer, the second argument would be the name, the data. The second one would be, the first argument would be the name, and the second argument would be the, is it a PDF? Let me open the, yes. Just, so the second argument would be the Uh, the first the first argument would be, as per the definition of this hello, first argument would be the name and by for the else part, and in the first part something different. So if we are getting mixed up, so the definition says that first one it expects a string or uh, the point that pointer for the characters, and the second one is the function pointer, and we pass the data to the function pointer, and we pass the function pointer to the data part, and so it get mixed up. And you the instruction, usually the instruction says in the dot text one, and the string and other user defined data would be stayed in the bss. The temporary variables that would be used for the stacks would be in the stack, and the program created memory would be stored in this heap. So this would transfer for the instruction from the dot text part into the stack, and from the stack it would get executed. And if the instruction would contains the payload that contains exactly uh, uh, the uh, the objective of the code that we want to attack, it will get executed and the system will get compromised. That's exactly the first type of worm. That's the recorded, documented, exploited that we know, that created. Uh, that's the first thing to be known of major vulnerability a worm can create. It's on 1980. Is it displayed here? Around 86 or something, even before the internet boom, uh, and the widespread of PC that we know after the dot com or other bus. So at the time itself, this has created in the MIT lab. It was released at the MIT lab, and it was able to replicate across all the systems. And they had to shut down the internet to uh, control the uh, worm. So you can imagine how how different it would be at the time. So no one would have thought about all of them would be in the time in the thing of like a concepts. And this was the first recorded or documented exploit about the worm, in which uh, yeah, virus program can spread, replicate and spread across all the devices, systems. It seems it can able to replicate across different architecture of the computer or different platforms. And they had to shut down the internet, and that's a big story behind it. And the person, the Morris, who has uh, spread the virus there was also the conviction went, and I think this would have created to enact the laws for security. And you can see these stories behind it, like he being pardoned for instead of giving punishment. So he was convicted, and then instead of going to jail, some kind of pardon or thing happened. And currently, he's a professor of MIT. That's as per the information I can get from the Wikipedia. So that's a kind of the code injection, the first kind of documented kind of attack. So what the shellcode would look like. So for example, um, uh, the basic concept is that you have the program. So for example, the hello program that we saw, and you inject code as a part of the data into the code. That's a like vulnerability, and the code gets executed. So how can we do that? Usually we can do that using uh, uh, by spawning a shell. So that's, if you can able to spawn a shell, then you have the complete control. And you can, if you can spawn a shell and then get into an interactive mode, you can give commands to the shell, and at the binary level, you have more control over the resources. And since the code would be running as the root privilege, the shell also will have the root privilege, and so you will have the complete control over all the systems. So the example that you see here, what do you think of the code that you see here? So that's what we meant by here the shell code. Shell code means spawning the shell. So because of the one UML architecture, you can be able to inject a code into the data part, and the code being executed in the being executed from the stack, or considered as a stack. So once, and if the shell code, if you can spawn the shell as a part of the code, then you will have the complete control. So an example here, you make a system call to the spawning the shell, exactly execbe, which has the code of 59. That's a system call, syscall table that we saw for our assembly language crash course and for the reverse engineering. So the 59 RAX, and then the parameters RDA and RSA will spawn the uh, shell. So the parameters that you pass for the spawning a process is execbe, and we have passed the argument as the shell, with the other two parameters for the RDA and RSA as null. Uh, this make a system call, and if this is sent as a part of the code, that exactly spawns a shell, and the shell will get spawned, and you can have a complete control by running the code. So, for example, if I can, in the previous code, instead of the function shell, if this is being passed, and it starts executing from the move part and then syscall, then you will get shell code being spawned, and then you will have a complete control over the resources. And we saw that in this slide of in this thing in which we are spawning the shell using execve, this shell is passed as the argument with a string. You can pass it in a different ways. That's what we saw here. You can pass it as a binary, as a byte, or as a string, or as a hex code that we show as the part of embedding the data. So you can embed the code part in different ways, uh, the- if you have the flexibility of using a binary, using an assembly language. uh, that's the advantage of coding in the assembly language. Okay, so what do you see here? Can anyone suggest what we see here? So the previous one is about spawning the shell. This is about the system call, but it's about sending the file. Um, it's The RAX is two. Two is for opening the file, and this call is for, so it's opens the it's open the file uh, as per the argument supplied in the RBX. I think the syscall for open accepts three arguments, uh, and one argument we pass the stack pointer, uh, and the other argument, second argument, so it would open. Yeah, so so this being passed to the RBX as part of the stack pointer, and the stack, so the RBX will push this. Okay, yeah, here the push here is, so the stack pointer, it gets pushed into the stack, and we move the stack pointer to the RDA and RSA the parameter to be the 0 for null, and then you make the system call with RAX equal to 2. That means it opens the file flag. So this, for example, the code would be run as the root folder, and so this would open with the root privilege, and you can read the flag. uh, so for example, if this is the challenge, you can use this to try to read the flag. And what about this code? Exactly. So the RAX call here would be the 40. 40 is for send file. Uh, if I can open, yeah, I'm trying to open the send file. So it just copies to the different file. Um, and you will pass the file descriptor as the arguments, and it will just uh, copy the flag, and you can read the flag. I'm just reading from the other desktop for clear, for the legible visibility. Can I see full one, full view? Okay. Okay, syscall is the last one. Okay. So it copies. Yeah. So it transfers the output file. That's the 40 cent collies with a byte value of 1000 bytes. So as you can see here, once you get so this is you are able to achieve using this is called, but once you get hold of the system by using the vulnerability by passing these arguments as a code. So you inject, if this code is injected as part of the data, then it will get start executing by reading the flag and then transfer the flag content uh, to the file as per this program. So here, after opening the flag, it transfers it to the file descriptor as mentioned in the RDA one. So that's essentially the shell code is. So you will have a shell code, the code that we saw previously for spawning a shell using the exe and the next one for for reading the flag file and then copying it or sending it to a different file descriptor. So how to build the shell code? If so we craft whatever we want. So for example, this is the 59 that we saw for uh, starting the process with parameters for the binary shell. um, so it's spawning the binary shell by initiating the process. uh, you create the shell code and then you execute it into a ELF file. So, what is a ELF file? It's an executable file for the Linux platform with the additional information about the system data and other kind of things. And then we will just dump the dot export alone to a raw code, and this raw code can be used as the payload to be injected as a part of the data. So, for example, if we can if we can code, for example, the same hello.txt, what I can do here is like I can copy the same thing. So let me open pwn.college. Are there any questions? No. Okay. So the challenges would be in the challenges, but usually you will have the challenges in terms of run. For here, this would be something different. So if I see ls challenge, you can see two files here. You can see from the you can the binary code and the binary code value in the C file. Um, Before looking at it, let's look at the hello world and how the shell can be smashed here. So if this is the shell code, you would copy it. I can, for the purpose of good display for the presentation, let me use the file folder and the other things here. So if I can see hacker, if you can go over it. So already I just copied one, so I can use. Okay, so this is about the shellcode. So I can create. Sorry, it should be. So I will open the shellcode. This is the one I think I used. Oh, I created. I'll just paste the code that we copied. I'm not sure. Okay. Global would be the first one. Am I, is it correct? Yes. So everything is good. And then we will compile it exactly like this. You can use different assembly language, but we prefer to use uh, this the same method that we recommended for the previous modules in the assembly language crash course and the reverse engineering part. So use the GCC with no standard library and the static. Uh, we will use the same thing here also. So and I will make it into an ELF file. Uh, there is a typo in global. Okay, so it's compiled, and use the same method for extracting the text part. So the ELF would be would contains the additional information also, uh, uh, and we need only the .txt part. We cannot read the thing through cat since it's a binary file. Uh, but we just need only the .txt part. So we'll extract only the binary code pertaining without the label and other kind of additional information in the doctext part alone using the obj copy, and we dump .txt to a raw byte. So we'll create a raw byte here. So obj copy. Um, I think equal to .text, and this will be shellcode 1.1 ROM from. Okay, I think this could be the format. So this creates the shellcode one raw, and this is what we have created, and this can be injected as a payload uh, to the any program that you wish to see. So I that's just before coming here, I just copied the hello 1.c. Else we can also copy here, and if you can pass the shellcode one as a part of the hello world.c or something, then you will have the uh, uh, code being executed as part of the thing. So, for example, the same thing happened. Same thing I copied just before coming here. Hello. So you can see here the same code that we saw here. And if we spawn the um, just and if we can compile such that there is no, we will see in the subsequent slides about how to uh, how the protection being enacted from the OA side and other things, such that it won't allow the stock part to get executed. So that's the normal part after getting know to being vulnerabilities that normally happen by being injecting a shell code into the stack. So to avoid that, for the purpose of our education, we have to compile using the GCC with hyphen is at the execution stack. So that, this allows the code in the stack to get executed. So we can use the same thing and compile for. So only if you use that argument to the command, then you can be able to compile a code or execute a code from the stack section. So I thought of copying, but it's simply execute stack. That's the additional one that we need. So if I say GCC, FNC execute stack and output as hello object file, you can see lots of warning. So I just gave hyphen W to get past of the warning displays, but still gets function warning would be shown. Uh, if you can, do you know what's why the problem with the gets function? So unlike the scanf function, gets function would look for the string and it will continue to get input from the string until it encounter the new line character. So this provides a potential opportunity for overflow, buffer overflow, and so uh, it you can get past the buffer overflow by having a long input, and hence it's not recommended to use gets and if the hyphen w also, that's not uh, get rid of that gets overflow, and it's recommended to not to use gets function. So once we get compiled, then you can run the shell code like the hello.c with so we already copied the shell code one raw that contains the raw part, and if this can be passed to the hello dot c, and you can have the sorry I'm executing the hello.c instead of the object file or the executable file. Okay. So we will read the created shellcode. That's the cat one raw and an additional cat, and we pipe it through to the hello as a part of the input. And it's expecting the first byte, I think. So that's the name part, I think. Um, and if we can give, I think if we can give cd pin as mentioned, ls. So that's the wrong one. That's the reason. So if we the I have to get rid of the one of them, and it has to continue to expect the cat. So I'm not sure. Once again, did I make any mistake with the command prompt? Yeah. So I think it went into the binary. So if I put ls, if you put ls, it should show. Whatever. I think some issue has happened with the shellcode. I think. Let me compare it again. But essentially, you would see that the thing get executed. Static. Are there any other thing? No. Shellcode one dot yes, and I think there is no parameter for output. Oh, we don't have time. Shellcode dot raw hyphen raw. I think so. Once you got it compiled, then you can run it. So you just pipeline the shellcode as an input to the raw. Something happened, but we can see the next week, or else you would be coming to know because that's the first challenge is about. Um I'm not sure why it doesn't show the subsequent one. Probably something went happened. But you can see here that you would be already be in the bin folder or some of the command get executed and it will get displayed as a part of the command here. And you can see here that you would be able to see and it's the yarn was also in the attached video. You would show that you would be able to get into it, and that's the challenges for the challenge also would involve the same thing. So the first challenge would involve, for example, so the challenges for this shell injection command would show as the baby shell level one, and it will read something like this. You can see here the challenges reads in some bytes, modifies them depending on the specific challenges configuration, and shell code rather than doing so. That's something a typical warning, but actually it's you would craft a shell code like we just now compiled the shell code for spawning a shell. Similarly, you have to create a shell code for something to read the flag, and then we have the file will be provided that would exactly load the shellcode into the stack and will get executed. So we'll see the some more uh, uh, code also. So this is how the you will create a shell code. For example, the first challenge, you are trying to read a flag and then get to know what is the flag. Uh, so you will this is what they mention about how to compile it into a ELF file, and then how to get into the raw file. So this raw is the payload that you could ideally inject into a vulnerable binary file. And for the competition, like CTF competitions, they would actually load. So there would be a loader for the shellcode, and you can load it um, into the tested code. So for example, this tested code will contain I should zoom it. I would create a memory and then load the shell code exactly here. So once this code is there in the shell code, you can just pipe your raw shell code into the test code and do it. So for our challenges, this would be the, for example, challenge baby binary. What's the challenge file name is called baby shell level one. And your raw code would be pipelined into the tester because it will have the line here. You can see here the less. So this raw code would exactly go into uh, the uh, the stack from the address stack pointer from here with the 1,000 lines of code, and this exactly loads the shell code. So you would be that tester would execute your shell code, and you will prove your understanding by the shell code for here. So this is about the running the shell code using specific loader function, something like that. And how to debug it. So once you start it running, so you can use this S trace. So for example, the previous one, you can use the S trace for, I can use the same thing, but it doesn't ask the previous one to get spawned. So once you run these uh, S trace, simply by running these S trace, you can have the if it is a since I am using the ELF, it's not a raw byte. So for ELF, you can use the S trace if it's run from the Linux as a standalone thing, and you can use the S trace to trace back the uh, uh, the process to know about the parent process and other things. So that's how that's what we show here. So use the S-trace to get to know about what happens if your code is not working. And ideally, the GDB is the first tool that you would be looking for to uh, to get into the reason for uh, hacking it. Uh, So you use the GDP and not the ELF file. You use the for our in the case of our challenge, you will run the challenges with the shellcode being passed on an argument, and then step by step you will uh, debug it for any vulnerability. So, for example, if we have to pass for our shellcode, then it would be uh, cat the shellcode one. It won't work because you have to read the flag here. Um, uh, Shellcode RAM and then the challenge. So it will show the shellcode and it will run. So here the shellcode doesn't show in doesn't achieve anything, that it just spawns a shell, and hence it doesn't achieve anything. What would be the case that you try to achieve the how to read the flag. So you have the loader here, and you have to create code, something like a level one or something. And then, so for example, EABC, for example, that's the shell code you have found, you have created, and you have to pipeline into the challenge one. So what could be the code that you would be for the challenge one? Challenge one is to lead the flag, and I think we have already mentioned it in the code. You can see here the loader and other details could be available in the C file. So it essentially has the loader that can input the that can load the raw file into the specific stack, and then the stack will get executed. So it's upon you on the shellcode to read the file, and this is executed as the root folder. So if you can create a shellcode that can read the flag, it will have the privilege of the root. So you can read the flag and then make it into, and then probably like we saw, send file to a different file and then read from that file, or you can display it into the standard out also. So that's what we saw. I'm sorry. Okay, I was showing Pan College, and it seems that it's showing only the PPT slides on the Twitch. That's because I think if I make PPT into a slide presentation, it will always show the slide, I think. So this is what I was showing. In the challenge folder, you will have the .c file and the binary. So the .c file is the loader that loads the file, and but essentially you have to create a shellcode that reads the file, and we saw here sample file for reading. This 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 reads the file in the specific location of the stack, but in our challenge, the stack, it automatically loads the stack. So you don't need to pass on the any stack related information, but uh, uh, but essentially you have to open the flag, like the method that adopted here for system call to for opening, and then instead of sending the file, probably you can read and write. So we have the system calls for read and write. So you can read the flag from standard in, read the flag from the file, probably using a file descriptor, and then you can output it into display, or you can use the send file to another file and read from that file there. So basically that would be the thing to flag, to read the flag for the challenge one. Any questions with this? And so we have only three challenges for the shellcode, and then we'll go over the memory type of injections in the next class. The second one is also would be the same as mentioned, but uh, probably with kind of some specific instruction, like for example, you should be, they would expect you to start after a particular offset of memory in the stack, or for example, in the byte level 3, you would see that they they expect you to avoid some specific characters, and you have to craft the shell code such that you fulfill that conditions. And the conditions can be more, it would display it in the shell code itself, or else you have the C code. So you see the C code here, in the ls. So you can open the C code, and you can see the um, So you can read the C code, uh, and I think I showed it in the here. Uh, you can see the C code, and you can get to know the information about it. So, for example, the second one, sorry, again, it seems that the slideshow will not showing my display here. So you can see the C code here. Uh, Depending upon the challenges, will have the specific requirements for the subsequent second and the third one. So that's what we will see in the next slides. For example, in the second and third challenges, you will have some specific requirement that we will ask. That's because usually we will encounter some common issues. For example, uh, uh, one second, just a second. Okay. Okay, so you can, depending upon the requirement, you can. The instruction is handled as a data. So you can, you should be knowing that you can transfer a specific byte word or d word or q word using the instruction like this. And um, and these are the restriction because we are doing a shell coding, and so there are some restriction. For example, string copy will end as it encounters space. The scanf will end as it encounters uh, new line or null character. So we will expect you, for example, for the string copy, if for the bytecode hacking, there should not be a null character if you have to use the string copy to attack. That's why in the second challenges you would be asked not to include the null character in the, I think it's in the challenge 3, I think. So these kind of specific requirements would be required for making the shell crafting, and that would be asked in the challenges also. So, for example, in challenge 3, they are asking not to include any null characters, and in the challenge 2, they would ask you to offset after the specific bytes of addresses in the stack memory. So this has to be taken care of in crafting the shell uh, code. So that's basically about the second slide that you would see in the pond tool. And the pond tools is a good tool, but for our initial 3 challenges, I would recommend using the same kind of compiling and making the raw shell code that suggested here. And the RAPL is also a good one that you can make use of it. And STS is very important too, along with the GDP. We need not mention about GDP. GDP is a important thing, and you would run the GDP using uh, our. So you'll you'll run the GDP, and then from the GDP you will configure for GEF using the GDP in it, uh, and then once the GDP is run, you can simply run, but this would be without the shellcode. So to pass the shellcode, you just run and use the single character. So run single character the shellcode. For example, the shellcode doesn't contains the uh, intended code, but you will run something similar to this as the you will just pass using the single uh, pass character. And then, as we mentioned before, like in the warnings, the OS proactively restrict running the code from the stack. Uh, so, so to prevent these kind of attacks, they make the code to be separate. That's the one of the, if you have use hardware type of architecture in which the code and data will reside in a separate memory, you would be able to avoid this kind of shellcode kind of attack. That's why the shellcode would proactively make it kind of restriction, in the sense they have the control that you can do for every processes, like the read protect, write protect, and execution protect. uh, Similarly, other kind of restriction are by default they would be implemented, but still you can be able to bypass it. That's what it being covered in the slides, and that you can watch it in the videos from the Professor Yan. Basically, you can also use the M protect features to bypass and then make it to work. Uh, Otherwise, currently it becomes very difficult to inject a shell code in the normal binaries, because proactively the OS makes sure that uh, the instruction part, it restricts the memory area uh, to not to execute or not to write or overwrite and other things, using the protection such as the read protect and write protect and execute protect, which you will come to know, which will see it in the videos uh, from the Professor Yan in the Pan College from the previous one. With that, I think I conclude with the shellcode injection. Next class we'll go over the memory errors. There are three, but there are only three challenges for the shellcode injection among the 12. But this is a good starting point to come to get grip with the binary injection, binary hacking. Thank you.